record on the cloud, okay. And then we can go ahead with the lecture. So any questions regarding previous lectures materials or the homework, which I can get from the Blackboard very quickly. I saw people submitting early in the morning today, probably working like through the night. Last night corrected some already. No questions. Okay, so you might have also seen that I posted the survey results, so we can discuss some of the comments later on. I really appreciate the feedback, and I think that's where basically we will go in. We discussed that to you know, put in some practical stuff in the class too. The other thing I wanted to say is also, I think one question in the survey was about Python. I think I didn't summarize that, but I had to look at it. I'm sure most of you are familiar with Python, but I just want to see if any students they need to catch up. Maybe I could, or I would definitely have them look some more. I'll post the materials and look those materials beforehand, so we don't explain very basic Python. Okay, so there's no questions with the homework. Okay, so let me ask you a question then. Is anybody familiar with the Google Colab or Google Collaboratory? Let me share my share.
We are.
So who is that? Go ahead. Tell us what the Google Collaboratory is. Did somebody wanted to answer the question? Or?
I can answer. So it's like an environment for Python, and you can code in here. And the good point is that when you're doing neural networks and you need like a high computational power, you can use the GPU for Google Colab. And also it's good because it's like Google Docs. You can share the link with like your friend so that like both of you can look at it at the same time.
Yeah, that is correct. And you get some free computational power, but you know, for big stuff, you actually have to pay like the Google Cloud, right? Even though they have, well, might try it actually. This gives me the idea now. They have those educational grants, so maybe we can get some free time if we are to do big stuff to share in the class, because they have this educational, if they still have it, educational grants. So have you used it before for your research?
Yeah.
Yeah, I have used it. Yeah.
Okay. So this is Arzu and Travel. Okay, great. So let me give the overview for the rest of the class. You might not know. For those of you who have taken Bio 425 last semester, we definitely seen that. So basically, as you mentioned, is an interactive, we could say an interactive Python notebook. So you can have, as you see here, and please at any point, as I'll be going through the browser windows today, if at any point the text is too small or anything is not clear, just please interrupt me and let me know so I can correct it. So it's an interactive Python notebook. Some of you might also know the Jupyter notebook, which is an open source software, and that's basically what the Collaboratory came from. The Google just got it and integrated the Jupyter notebook. Google picked up the open source project and integrated in the Google Cloud. So as you see here, you can have interactively text and code. So you have to log in with your account. So you have to have a Google account. I'm sure all of you have, or you can make them like 10 seconds. And then we will use it in the class to practice our Python and also complete the homeworks and submit the results of the homeworks. And I'll post you can find yourself too if you put it on YouTube, like hundreds or thousands of videos explaining the Google Collaboratory, which says like what the things do there. But basically, it's pretty simple. Like, you say insert code cell or text cell, and then you write your Python code, and then you just run the cell by hitting enter. Sorry, the play button, and then after that it gives you the results. I think this one just printed out a number, and then this can be as big as you want. They can have like different sections and so on and so forth. So that's something you can practice yourself. Let me see. Okay, how can I enlarge? Just give me 1 second. I need to enlarge the window here. That's not it. So here, after years using Zoom, I'm still trying to learn. Anyway, it doesn't matter. So this is with the Google Collaboratory. Now, there's another thing which I recently discovered, and if someone knows in more detail what this is, I think it shares a lot with the Google Collaboratory in the way it can be written. But I think it's something that's, I guess, a little more interactive. I would say it's like a Google Collaboratory interactive Python code and text pages. But you can have, I guess, multiple of those in a kind of a slide format. And it's called the Google Code Labs. So I guess it's one more level up from the Google Collaboratory. And I would, for those of you that are interested more, just go, I'll post those links. We'll go through one tutorial today, which is very relevant to what we've been learning in the class. But when I post that link, you could get the codelabs.developers.google.com, and I could do that now actually. And when you go there, you'll see, where was it? See, my internet is kind of slow. That's what I was saying. So I need to fix it. You'll see tons of stuff, hundreds actually. And I think there must be a search button, yeah, right up here. So you could search for whatever you're interested topic to learn, and you could explore more beyond the things we learn in the class, even though some of this stuff is going to be like very, very specialized artificial intelligence stuff. But I just wanted to point you there if somebody is interested to explore. Okay, so the one thing we've been doing today, so or in general, just let me say, so I'm going to spend, I think, a couple of lectures going through this interactive mode that we're going to be doing today. So I'll show you more applied stuff as a follow-up to what we've been discussing. Of course, so far we've covered the the feed forward, all the processes, computational processes going forward on the computational graph of feed forward neural network, multi-layer perceptron, however you want to call it. We haven't covered the backpropagation, which is very important. And I'm hoping to cover it at the next lecture. So maybe we'll do one full lecture of today of that interactive stuff, then a half lecture of more interactive stuff next time, and half more lecture of the backpropagation, because we need to understand like the theory behind it. And then we'll see how we go from there. Definitely, by mid-October or earlier, I want to get into the coding as well with Python. And we're going to keep the theory at the same time. Okay, so let's start here. Overview, funny comic here, deep science, deep code. And it just gives you, like I said before, it's as an interactive presentation with multiple Google Colab interactive Python notebook code slides here, 15. I haven't actually made one of those. I made many Google Colabs before in classes I was teaching. I would be interested to see how you compose those. And I think maybe we will leverage this stuff. Definitely the Google Collaboratory for the homeworks, as I mentioned before. So the topics for today, or not today, we'll cover one or two more things, but the thing that we're seeing here, let me enlarge the text. It says what you learn, what the neural network is, and how to train, kind of know that, how to build one-layer neural network using Keras, a little bit of code, maybe we'll go over it, maybe not, layers, learning rate schedule, and convolutional neural networks, which is a new concept we're going to introduce today. And we'll touch a little bit on that stuff, but for these topics, regularization, dropout, we'll definitely cover it much more deeply in the theoretical components of the course. And again, I'll post links on YouTube for YouTube, how to use the Google Collaboratory, but then it basically says here really quickly what I said before, how to run cells with the code, and so on and so forth. You don't need to worry about that now because I'm not assigning any code problems yet. Okay, so in our stuff that interests us, training a neural network. I'm sure you all remember the minced handwritten data set that we mentioned in the text. So basically, this is a very simple handwriting recognition data set. And you'll see, like, I also have a paper for today. So what I want to do is explain like how we do the hand recognition, the images here with the traditional feed-forward networks that we've been using. Then we're going to see the convolutional neural networks, which is another way to work with those images, especially three-layer, three-colors images. And then I have a paper how the convolutional neural networks are applied in biological problems. And maybe I'll scroll through the paper quickly, but that's something that's going to be as a homework assignment for you to, kind of dissect and answer questions on it. But if you understand that stuff today, then you'll be able to apply it on the biological aspect. Yeah, I think I'll continue trying to assign one paper in every lecture with biological applications and follow that mode. Okay, so back to the minced data set we had here. Very simple data set. I'm sure some of you are familiar with it. If you remember, it's 28 by 28 pixel images. So basically, here where my cursor is, and please let me know if my cursor is not clear. Let me see. Just give me a second. I'll go to the Windows settings and try to enlarge my cursor size. Change cursor thickness. So maybe I can make it bigger. Mouse pointer, not cursor, pointer size. Yeah, it's definitely bigger. We can change the color too. So that should show better now on the screen. If something doesn't come through, please let me know. So each one of those, what it shows you here is one of those images, right? 28 pixels by 28. I mean, you just mash them together, but imagine like its digit here is in a little rectangle, 28 by 28 pixels image, right? And that's the data, the input data. And try to remember in the text before how the images are coded by pixel values. I mean, it can have, I think maybe it's in one of the next slides too, but I'm sure you can visualize it because we discussed about it before. It's a 28 by 28 matrix. Each cell has a value. Let's say, I mean, you can say it either way, it doesn't matter. You can say full dark black value is 0, fully white is 255. So the pictures go from 0 to T55. And then all ranges is between for the values of gray. So we can also simplify it if we want to say that it's just black and white, right? 0 or 1 for the pictures. Either way is fine. So this transcript, we're doing it, but I'm going to try to hide it because it drives me nuts to just see what I say here in the transcript. I'll put it in a corner here so I cannot see it. Okay, so okay, so this is the input data, the pictures, and then the digits are the actual labels, right? So we see one more thing here, which I think we touched upon earlier. Instead of having the labels 1 and 0, I mean, we've seen other labels in the homework when I had this thing with the one hot encoding with the birds or whatever that was. But here, essentially, can somebody tell me how many labels, possible labels we have for the digits?
10.
10.
From the 10 digits from 0 to 9, exactly. Okay, perfect. And actually it's written here, so you could just read it probably off the text. Okay, so that's the 10 labels. Oops. And then this is the training graphs. Don't worry about it now. They come up in the later one of these later sections here. So I will explain them. And it's loss graph. So we'll explain those. And then I guess what he did here is probably like I don't know, a shallow network, or meaning like just using like one hidden layer or something, or just did like just a couple of epochs, so it wasn't really learning the weights, and he got a lot of wrong predictions. So he just shows that you know, this 7, it was thought to be a 9, this 7 was thought to be an 2, and so on and so forth. So that's probably you know, he just did a couple of epochs of training, and then he got the predicted values for this short cycle of training, and then that's probably somewhere up here where the loss is really high, and then you know, he shows you the actual predictions, which is like totally off. Basically, the predicted labels, they're down here. The actual data is up here. So you see like this one is predicted as 9, like totally off. So basically all of them are red. So they're totally off. And he says like, yeah, 120, 168 in red and short. Okay. So tensors, I don't need to explain. We covered before. Essentially, tensors is stacked arrays together, right? So a color image, you would represent it as a 3-dimensional tensor. If the image is 28 by 28 color image, you would have 3 arrays stacked on top of each other, 28 by 28 each. Okay, let's go up here. So some definitions which we already covered, layers of neurons, dense layers, meaning like the many lines, like we've seen before, we covered those, and convolutional layers, which is also dense because they have many lines, but we haven't seen the structure of those. We'll see them today. One-hot encoding, we covered. Softmax is something that we've seen in the text. It's just another activation function, which, unlike the logistic function, which is a slope, it's more like you would say a probabilistic activation function. We don't need to go much into the details of it now, unless when we get back to the theory, we want to understand how the functions behave, because function choice for the logit is very important, right? And I'll post like a text today with a list of the most common used functions, and the softmax is in there. But if you're going to go into the mechanics of this function and to understanding all the choices, then we can do that later on in the theories. So here some of the code. Basically, we'll go over those codes when in the next lectures we get more and more into the coding. But if you want to, I'm sure some of you are familiar with it already based on what I've seen on the survey feedback. But that's what happens in their similar class. For some people, we have to be patient because you know the stuff already. And also we have to cover everything in more detail for those who are not familiar with the frameworks. But just really quickly here, he's basically building the neural network. And you see how simple is with TensorFlow. TF is the short for TensorFlow. Keras. So in Python, basically that specifies the top level libraries, the TensorFlow. And then inside this is the Keras. Basically, Keras was a Python library. There's two main Python libraries. I mean, I'm sure there's others too, but one was the Keras, and then the other one is the PyTorch, which we're not going to cover in this course. We'll focus on TensorFlow. But Keras was absorbed into the TensorFlow framework, and then Google did a lot of the development of the TensorFlow, and then they open sourced it. So that's why you see TensorFlow in the higher level and Keras, which is absorbed in the TensorFlow. And then he builds a sequential model, which means like the stuff we've seen, right? An input layer, a hidden layer, hidden layer, hidden layer, output layer. So that's a sequential network. Essentially, it means feed-forward network, even though we'll be seeing on the slide kind of like, instead of seeing it like this, like we've seen it before, from now on, we'll be seeing it like that. And that's how we write it in the code. Basically specifies flat input, which you'll see in the next image, and you're familiar with it already. And then it adds hidden layers, dense layer, meaning all connected, how many neurons, and the activation function, the RELU, which we've seen already before. So two of those fully connected, lines connecting all neurons against each other, not within the same layer, remember that, but from one layer to the other, right? We don't have connections within the same layer. 200 neurons in the first layer, 60. Don't ask me for the choice of the number on the second layer, and 10 in the final layer with a different activation function, being the softmax. Does anybody have any hint why is 10 in the final layer? I mean, I'm just jumping a little ahead, but I just want to take a break from talking. Go ahead.
Because there are 10 classes for their digits.
Exactly. So in the final layer, you always have to have, and that's something we remember going forward. You have to have as exactly the number of neurons for the classes of that you have in the output, right? So 10 digits, 10 neurons. And of course, in the input, you have the input neurons, right? Which, I mean, we've said before that the input neurons must match the dimension of the input data, but on the TensorFlow, it's not exactly like that. It's basically like you specify the first layer of neurons being 200. That's what you chose here. You could choose 1000, but then the pieces of the input data, they just get mapped automatically to this first layer, and we'll see that in the next picture. So you don't really need to, when you write code, you don't really need to worry for what we've been seeing on the theoretical aspect, that the number of dimensions that we have in the data, we have to have the same number of input neurons. There's not really input neurons when you write the code. It just always, the data goes directly and fed on the first hidden layer, right? So that's one thing to remember. And then he compiles the model. Compilation meaning essentially like kind of run this code and see if everything like works out correctly. You know, if, for example, some mess was here with the dimensions of the input data and the connections, it will probably complain the code at this stage. Now, optimizers, we haven't talked, because I haven't talked about bug propagation. Loss, do you remember we talked about some loss functions? Can you tell me which was the one we've seen in the text? I don't think we've seen this one, but which was the loss function we had in the text? It was the kind of the average. Sorry, go ahead. Go ahead.
I think in the text that was the sum square mean square sum.
Yeah, some averaged sum of square differences, if you will. I don't even remember the correct definition, but it was a very standard metric. But one you'll see used a lot as loss is the categorical cross entropy. And that's what he specified here. Actually, if you read the documentation of TensorFlow, you would see that you can specify as loss function the sum of squares, right? But it's a much more simpler, and it's not used in practice. And we'll go over those when we get into more back to the theory. And metrics is something that it would, I think that's the graph, if I'm correctly, or it just prints out as a number, is basically the accuracy of the model. There's many metrics you can use. And then after the compilation is fit the model, and here has like 3 dots because he doesn't write the whole code, but essentially is after you specify basically model being the structure of your neural network, and then you compile it, meaning that it's get checked that everything is lines up correctly. Then fit with the data set means that you throw the training data set to it. And there's like other parameters here as well, which is like how much of the training data set to keep as validation or training, and so on and so forth, right? So he skips all those. Question?
What about the like when we see the 200 go up? Can we go up?
Mm-hmm.
How do we come up with the like how many new nodes we need for the the 200 ReLU 60 ReLU?
Yeah, like, you could put 1,000, you could put 20,000. So it's not, that's what I mentioned before, like you could have put like 1,000. So it has to do, I would say the general idea would be like you wouldn't put 2, right, for 10 digits. You need to have definitely like more than 10. But more means like better, because you know each neuron has the summation and a non-linearity, right, based on the non-linear function we choose, whether that's ReLU or TANH or whatever the other functions we saw. And the more neurons, the more non-linearities. And essentially, the power of the neural networks, the artificial neural networks, is the and also the neural networks in our brain, is that they operate as non-linear units. So the more non-linearity you add, the more classification you have. Of course, this opens the question that, okay, we can add like 1 billion of those, right? But of course, you would think like after some point, there's no gain. So you want to put, the answer is like, you want to put enough that you have enough discrimination power for the type of data you have, but you want to try to be as how you say, as lean as possible, because if you add like 1 billion of those, your computation, all those summations and applications of the logit function to the logit taking place in each neuron, it's going to happen 1 billion times. So that's a lot of computational power. And then you only need like 1,000 to discriminate what you have in your data set, to classify what you have in your data set, then stay at 1,000. And of course, it's a little, you know, trial and error process, right? And you would start with smaller numbers, and if you see like you don't get like good metrics, then you increase the numbers, right, slowly.
What's the similarity to the human brain, like the number of neurons per layer, let's say?
I probably have to ask like somebody who knows the wet lab neuro aspect. But I know you probably know too that the human brain has 1 billion neurons inside. But definitely the human brain, it doesn't have, I mean, it has all-to-all connections in a sense, but it's not like asymmetric connections as we have here. And also it's not a static network, because the learning process, and that's as far as I know as neuroscience goes, is about neurons like forming new connections, right? In the
So
brain.
everything is connected, and there's no such layers. Like you can't. It doesn't really have like, let's say 1 billion the first layer, then 10 billion the next layer. It's more
I
like
think
a whole.
I think 1 billion refers to like the total number of cells in the brain, neuron cells in the brain. But the number of possible connections between the cells is astronomical, essentially. But what I was saying before is that, you might have, and again, don't quote me on that because I'm not a wet lab neuroscientist. You might have like bundles of cells. That's a bundle here, is the actions, and there's another bundle in the connect, and it kind of looks with what we have here in our artificial neural network drawings. But I would say like there's also like many random connections here and there, so it's not as structured as the neural networks we see here in the human brain. That would be to the best of my knowledge as I understand it. Otherwise, it would behave very mechanistically, right? So I think the power of the human brain is like the very random connections. And of course, unlike that we see here, the static connections, the brain always like gets rewired, right? Based on the learning, based on the age, based on how you train it, basically, with like.
Also that human brains tend to have like habits. I think that's like probably when that's like if you're training a neural network and the model gets stuck at some local minimum, it's similar to the brain. Like we get stuck at some kind of habit and we try to get out of that.
Absolutely. Yeah, and that's exactly what the weights being strengthened between neural connections in the brain. And that's like very similar to what we do in the artificial neural networks, where we sort of learn the weights and strengthen the connections between neurons that perform well on our input data, right? And that's, I guess, part of the learning process, right? You strengthen the connections for a specific task, and it's like a habit, but I guess we would use the word training. You strengthen specific connections, which makes you good at a specific task, right? Like when you learn to play music, or you learn to like do crazy turns on a skateboard or something, so you learn to like coordinate all your muscles and stuff like that. So yeah. Okay, so back to our mechanistic stuff now. This is what I've seen before. And can somebody explain to me how we get to this simple question, how we get to this 784 pixels?
Well, that's the number of total inputs when you have a 28 by 28 matrix of pixels, right? Each one is value 0 to 55.
Yeah, so essentially this is 28, 28, 28 each row. So you just get the first row, you put it here, 28 of them. Then you get the second row, you put it here 28. So you just get the first row, put it there, get the second row, put it next to it, get the third row, put it next to it. So you just stack all the rows linearly, right? And that's what I think was in the code too. That's what the flattening does, right? So your input shape is a 28 by 28. So you're just going to grab rows of 28 each, the first one, the second one, the third one, and just put them next to each other. So it just flattens the image from a matrix of 28 by 28 to a long vector of 784. 28 by 28 is 784. And then, so the first layer, I mean, he shows here like 10 neurons, 0, 1 to 9. But as we've seen here, the first layer was 200. So here we have 200 neurons. And how many lines would we have coming in each neuron? What do you guys think? Let me grab my water really quickly while you're thinking. So how many lines coming in each neuron? Would be 200 lines. Or 784.
The number of the second layer neurons. That's how many each come out of each neuron.
No, let's say let's go by the code, right? So the first hidden layer is 200. I mean, he shows here like 10 neurons, but let's say this is 200. And then we have 784 inputs, right? Because the purpose of flattening the image is to fit the structure of the neural network, right? So essentially our input, like we were saying with x1, x2, x3, x4, 4 dimensions. Now we see x1, x2, x 784. So 784 dimensions, right? That's our input. And then on the first hidden layer, we have 200 neurons. And it's an all-connected neural network. So what happens in an all-connected neural network? Each neuron gets a line from each X, right? That's what all-connected means. So we have 784 X's. And okay, we have 200 neurons. Doesn't matter how many we have. The question is like how many lines each neuron gets.
Oh, you multiply both numbers. So 780, 200 times 780, whatever it is, 784.
Yeah, so that's the total number of lines, 200 times 784. But on each neuron, that's what I want you guys to have clear. In an all-connected network, each neuron will get a line from each piece of input, right? So each neuron will have 784 lines. Does it make sense? So it's this neuron here. It doesn't matter how many neurons we have. Might have 200, might have 300, but each neuron will get, in an all-connected network, you will get a line from each piece of the input, so we'll get 784 lines. And if, like you said, if we have 200 neurons, the total number of lines is going to be 200 times 784, right? So that's what he shows here. Now back to how we do things with matrix multiplication. So this is the weights matrix. So basically, yeah, he says he represents everything as matrix, right? So let's say, I mean, the means data set is much bigger than that. So let's say we had 100 images is bigger, but each one image per line, all right? And because the images are 28 by 28, we flatten to 784. So each line is going to have 784 columns. That's what he says here, 784 pixels. And then 100 rows, so 100 input images at 784 pixels each. The flattened image, like we mentioned before. And here he also, it's a schematic, right? So it doesn't follow regular notation, but here is the label. Remember the graph of a function, right? Where you have the input data, the x1, x2, x3, and then at the end, you have the label, right? An additional number. That's what he shows here. So here you have x1, x2, x784, and you could have the label in the end. I mean, he just indicated here in a schematic, which is the label is, this is the image for digit 8, this is the pixels for image for digit 4, the pixels for image for digit 6, because this is a training data set, so its image has associated the number with it. It's a handwritten digits image, but we've added a tag, if you will, what's the true digit that the image represents. And he he hand draws it here, but it would be like the real numerical label, which we can use for the training. And again, what the purpose of the whole training is to after we build our neural network, for the system to be able to automatically predict the correct digit from the handwritten image based on the training that we did with the data that were handwritten images, but they were labeled, right? Okay, so any questions regarding that?
Do you mind if you can like draw on the screen? Like there is I think in the Zoom, you can like actually draw like something like this, input, like whatever, and then it goes on, like how many layers, and like, because I'm confused with like, okay, there is a layer 0, 0, 0, 2, 0, 3. I don't know how, like, okay, these are in a picture. I don't know how.
Are you drawing that stuff now? And I see in pink. Okay, now it disappeared. So, yeah. I don't know what you were trying to do, but which are you referring to, the code or?
Not the code. Maybe it shows the
Which part are you confused?
The layer part, layers, like
this one?
No, matrix multiplication.
This one. This schematic is what you're asking. Okay. Yes. Yeah, I was gonna explain that, but let me ask beforehand if there's any questions in what we discussed so far. One thing you need to remember, this is not a textbook, right? And of course, textbooks have errors too, which we've seen before. And it's probably written by developer, kind of fast too. So, I guide you through that. Like some things, they don't like click with each other, right? So here, like, he shows like the code, which has the first hidden layer with 200, second one with 16, and the output layer with 10, but he doesn't show that in this picture, right? Probably maybe, for saving time, but also for clarity too. So that's one thing that might be confusing to you. Just ignore the 260 for the code now, and let's say it's a very simple neural network. That's actually this one here and this one correspond to each other, so we're good with that. We just need to forget the 200 and the 60. So what this is, a very simple neural network with one layer, just the input, and then one hidden layer inside with 10. So he basically just uses exactly 10 neurons in a single hidden layer, and that's what the matrix multiplication is. And I will explain the matrix multiplication, but with what I discussed so far, you can even ask for the code too. Is there any questions before I go?
I still want to
forward?
understand this picture. Is it, so you said it's a hidden layer, but it
This
seems
one?
like,
This one
yeah.
here? Okay.
Yeah, I don't actually see how, yeah, this works. There's an image input and there is a 10 columns. So I just want to understand what they're trying to depict here.
Yeah, so one thing to remember, unlike what we discussed in the theory, input neuron layer and output neuron layer, this doesn't exist in the code. And so there's only like hidden layers in the code, right? So essentially, if you wanted to correspond to the theory here, I'm showing the code now, you would have one input neuron layer, which it's not specified in the code and it's you never see it, and one output neuron layer, which is also not specified in the code, right? And again, this code doesn't correspond to these picture. If it was to correspond, we'd have to delete those two that I highlighted here, and then it would correspond to the image. So basically, just what I highlighted in blue here, just delete it in your mind. So that would be the definition of the network. So basically, this network would be a single hidden layer network. We don't have like input neuron layers and output neuron layers. This doesn't exist when we do coding. So we would just have a single hidden layer on the inside with 10 neurons, and each neuron, as we discussed before, getting 784 connections. So our input data, the image 28 by 28, flattened by taking 28, 28, 28, put next to each other, row by row from the image. That's the input. And then the network has a single hidden layer of 10 neurons, which each one gets all the inputs. So each one of the 10 neurons gets 784 lines or 784 x's, x1, x2, x3, x784. And then it does the summations, which we'll see how it works with the matrix further down. And then it does the application of the logit function. And then it just gives an output, which then we get. And with a loss function, we compare to the true value. And that's basically it. And here, like, he uses the softmax as a logit function. Does this make more sense?
No, for the matrix that in the animation, I just wanted to understand what the animation was trying to say.
The matrix, I haven't explained it yet. I will go to it.
Oh, okay. All right.
Yeah, I'm just asking, like, everybody for all the stuff I have explained so far, if there's any questions. Which some probably there wouldn't be, because we've seen that stuff in the theory, and then we explain again in detail now. So it should be, I hope, clear for everyone. Okay, so now for the matrix, basically. So, actually, is Junho, right? Can you tell me? You tell me what's your confusion, and then I'll go ahead and explain.
Yeah, in that animation, the if you go down a little bit, there was a animation like showing 10 columns with the L whatever.
This one, right?
No,
you see that the lines.
Yeah, the animation that you showed us. Yeah.
It's on the screen now, right?
No. If you have to go down a little bit.
This one? I didn't get there yet.
I think the screen is frozen.
Oh, the screen.
That's what I'm trying to figure out. Yeah.
Oh, yeah, screen was not moving.
Okay, I think my Zoom has crashed. Okay, So everybody stay put. I'm gonna get out and come back in again. Okay. So don't hang up. Yeah, my Zoom is frozen. I don't know. Maybe I should stop this transcript thing, because I think it's gets a lot of artificial intelligence to transcribe my accent in my computer. Maybe that's what crashes them. So I'm not gonna start this transcript thing, because I remember last time when we had the transcript on, the Zoom crashed again. And I've been using Zoom in this computer without the transcript for quite some time, and I never had a problem. So I think we're not going to use that thing anymore. Okay, I'm going out. You guys stay in. I'll come back. I think cannot even go out. Okay, I'm going to use the task manager, and then I'm going to kill my Zoom.
Now yours.
Now it moved. Yeah.
It moves. Yeah, but I still see the Zoom kind of frozen. Do you see the page like moving?
It's
Yes.
there's a big delay now.
Yeah, so I need to restart it. So let me do it. If the if by any chance the meeting like drops, then you know, just I'll restart and then you guys log in again. Okay, there goes the Zoom. Can you hear me?
Yes.
Okay, perfect. And I think, let me see what I have. Transcript. How do I stop the transcript?
I think it's in the bottom.
From live transcript, disable auto transcription. Okay. Yeah, so we're not gonna do the transcript. Then we record the lecture. If there's anything in any section of the lecture you don't understand when you review it, then you know you can post on the forum and I can explain, because I'm kind of worried. Can you see the window?
Yeah.
Scroll smoothly.
It's
Or
not going
is
to be
the scrolling-
perfect, but
but it comes clear, the image, right?
yes, it's clear.
Okay. Yes, and if we scroll, let me test it a little and then we can go ahead. So now maybe it's a little blurry, but now does it come clear?
I think it's clear enough.
Clear enough. Okay, that's good. All right, so we'll try not to scroll very fast. And then, yeah, I think it might have to do with the network connection too. That's why I'm going to plug the laptop in, because I think there's like the data going to the cloud from the Zoom recording. There was data going like with the live transcript, because that audio has to go to the cloud, get transcribed, and then come back, you know. And then also the data going in. So maybe that's what crashed it before. So we have the transcript out. Let me check the recording is still going. Okay, perfect. And then we can explain that. Okay, so Junho, you were saying you're confused on the matrix on what aspect?
Yeah, so it seems like it has 10 columns, and once it start to multiplying, it is start to creating the L00, L01, these layers. Like I wonder what is the so it seems like we have a lot of layers by multiplying.
So let's
I want to know the size of the, like, yeah.
Okay, so this matrix multiplication that you see, and I don't want to scroll up, but maybe you can have the page open on your computers. I guess I haven't posted, but maybe you can copy it from what you see on the address bar. But I'll post that on the Blackboard. But if you scroll up, or maybe you remember already, is the matrix multiplication, is the single matrix multiplication for that single layer we have. So the network we're looking right now is a single hidden layer network in a single matrix multiplication. You might be confused that it uses the L number, but that doesn't correspond to layer. It's a single layer. I don't know why he used like
So what
L
is the
number.
notation is trying to say? L00, L01. Once you finish one layer multiplication, you start to creating L00, L01, things like this. What is that indication?
I think it would be, I'll explain another way, but let me say on what you just mentioned. I think it would be better if you use like N, which would correspond to neuron 1, neuron 2, neuron 3, neuron 9. So let me explain that. So this is the, you've seen that before in the theory, like the way we do the calculations, matrix multiplications. So it's like the input data times the weight matrix, right? Because the summation you get is like the inputs times the weights, because you have a line coming from each input and each line has a weight on it. You need to multiply the input with the weight, right? Because the weight is what adds the significance to that part of the input, right? So it's always an input matrix times a weight matrix, and that's what we see here. That's the input matrix times the weight matrix. So let's talk about the weight matrix. What kind of dimensions does it have? What is the dimensions we see here? How many rows, how many columns?
10 by 704.
So 10 columns, which is the number of
Neurons.
The neurons.
Exactly. And 784 rows, which is the number of the input data, right? So the weight matrix is pretty simple. Number of, and this, remember, this is a matrix which is a learnable parameter matrix, because the weights is something we're going to learn going through the epochs of the training cycles of the neural network. I mean, this is pretty simplistic neural network. So we have each column is for each neuron, and I don't want to scroll up, but remember 10 neurons, and 1, 2, 3, 4, 10 columns, 10 neurons, and each neuron has 10 lines coming into it. I'm sorry, my mistake. Each neuron has 784 lines coming into it from all the X's, from all the inputs. So it's going to be for each neuron, for each of the 10 columns, it's going to be, don't draw on the screen, it's going to be 784 weights.
I just want to confirm if what I understand is correct. Is that okay?
I don't see what your drawing is, but please, in the future, before you draw on the screen, just ask me first. But ask your question. Go ahead.
Okay, so you're saying there are 10 neurons in the hidden layer, right? So it looks like 784 input goes into the like 10 neurons, and we see that here's like all of this fully connected to next to like 10 each like neuron. Is that what this multiplication is indicating?
Yes, that is correct. Yeah, so you basically, if I understand your drawing correctly, you just flipped it on one side and you just draw like, you have the input here data, and then you have like 10 neurons, and for each neuron you get like 784 lines.
Oh,
If that helps you understand better to look at it this way, that's fine. Yeah.
Okay, thank you. I'm just more familiar with this diagram because we've been practicing in this way.
Exactly, that's what we use in the book. Yeah, but actually going in all the tutorials you see on the web, anywhere, it's going to be the other way around, the vertical. But you think of also about like matrix transposition, right? It's the same thing. But here is pretty simple. And please, anybody ask me questions if you might have. 10 columns. This is the weight matrix. The weights we're going to learn. It might be initialized as random weights. and then keep updating as we go forward, do the calculations, then seeing the error and doing back propagation, and then adjusting the weights based on the results of the back propagation, doing the calculations forward again. Back propagation, I just described 2 epochs, 2 cycles, and then doing that thing all over again until we settle on some weights that we minimize the error, right? And again, that's the weight matrix, 10 columns, because we have 10 neurons, and each neuron has 784 lines going into it for the 784 inputs, the X's that are going in, and that's the 784 lines that you see here. Right, so if you want to think about the calculations we were doing before, this is, he says the data set is 100 images. Each image is flattened as a long 784 vector. So it's going to be a 100 by 784 matrix. And this one is a 784 by 10. So the matrix multiplication for those two is going to be a 100 by 10. So this is going to be the result that he shows here.
Okay, so each iteration of these X's, how he's showing the lines going from the matrix on the left with the flattened images.
Mm-hmm.
He has those each going on the first row, but is every iteration supposed to be a successive row?
No, we only see one iteration here. This matrix multiplication.
Well, how come each one goes to the matrix on the right? Every time he does it, it goes to a different column.
Because
it's not
it
the
is
same row, is it, for every column?
It's because it's going to the different neuron. Remember, 10 columns is a neuron.
Uh-huh.
And each row input is going to the different neurons. So we have that animation.
Exactly.
Okay. Oh, okay. It's just a little confusing because it's.
I think the animation is wrong.
Right.
It's a little bit off. Yeah.
It's supposed to be the first row times everything, and then the next row.
Yep.
It's
yep.
just not
Okay,
right.
that's why I was confused by this.
Yeah.
Image.
Yeah. Yeah, and then let's not get hung up because, you know, again, this is like a tutorial, it's not textbook. And tutorials, these kind of tutorials tend to have a little more errors than textbooks. But what I want you to get is the general idea, how things work, and also to map the things we were discussing before to the more practical applications. But one thing also to remember here, you see for like a data set which is 100 images, and very small images at that, 28 by 28 pixels, you see how many numerical computations are involved. For a very small neural network of 10 neurons with a single layer. So if you keep adding like more and more layers, more and more neurons per layer, the data, you already know that, you know, we have thousands of images if we want to train neural networks, and the images is definitely not black and white, just black and white, they're color, so 3 layers, and they're not 28 by 28 pixels, right? We're talking about megapixels that our phones get, and that's the standard now. So you can imagine what kind of data sets we're talking about. But just for this very simple small one, you see that it's a lot of numerical computations, and now you realize why you know, these kind of computations take a long time. Okay, so broadcasting. Try to replicate the small one as much as needed to make work. I think that has to do with adding the bias. So essentially, what it says, and that goes down here, is the screen, the scrolling come out well? Can you guys see clearly, or is it
Yes.
frozen? Okay,
It's on the
perfect.
softmax.
Softmax, and then there's the you can see the multi-layer network as well, right?
Yeah.
Okay, perfect. So this broadcast, so he shows here the the whole multiplication and matrix algebra notation. So that's what I mentioned before, our image matrix, 100 images times 784, and then multiplied by the weight matrix, 784 by 10. So it's going to result in a 100 by 10 matrix. And then he adds the biases, which is one bias per neuron, so it's like 10 biases. And what he was saying about broadcasting before is that because the bias is going to be just a single vector, and then to add that single 10 by 1 vector to a 100 by 10 matrix, you're going to use the broadcast, and we'll say that when we go in the code, that's pretty standard stuff, to essentially add this vector to each of the 10 lines of the to each of the 10 columns, I'm sorry, of the resulting matrix here. But yeah, we've done that in the theory, but essentially it just says that you need to add the bias. It's actually lines, I'm sorry, I'm just keep correcting myself. I tend to get tired as we get towards the break. But because it's a single vector and we have like multiple lines, you just need to add the same thing on each line. So basically adding the bias to every neuron. And then our standard like summation represented with matrices and addition of the bias, and then that forms the logits. And then on the logits apply the softmax function, which is a different logit function than the logistic function or the tanh that we've seen before, but it's just another function that it's applied. And then matrix dimensions is going to be both on the both the same on both sides. The function doesn't change anything for the matrix dimensions. It just gets applied to every element of the matrix as we've seen before. So our predictions, it's also going to be a 100 by 10 matrix. So essentially, what the 100 by 10 means, if you're confused, for that is that is 100 images, right? That's why it has 100 rows and 10 columns, each column for 1 digit, and we had 1 neuron for 1 digit. And then each column is going to say the predicted digit. Now you'll see as we go further in tutorial, it's not going to be as we've seen before that. Remember, it had the digits in red. It's not going to be like saying, for example, predict digit 5 where the digit is 3. It's going to be some different numbers, and that's how it's used to calculate the error. But I think we'll get to that after the break. Let me show a little bit more here. So what you see now on the bottom of the page is kind of more of a real case network, because before we just had with a single layer with 10 neurons. This wouldn't do much of a classification. I mean, now he adds like more stuff than he had in his code, because his code he had like 260 and 10, I think. But now he has some more stuff. But again, it's all about explaining the schematic. But remember, the input always matches the data, 784, and the output matches exactly the classes we have. And then in between, we can have as many layers as we want. Usually, for this type of standard classification, I mean, this is a teaching example problem. You're going to see like a thinning as it goes down, but here we have 200 layers, 160, and 30.
What is a broadcast? Sorry, you when there was a broadcast on all line.
So basically, the X matrix by W matrix, it's going to be a 100 by 10 matrix, right? Because it's 100 images and 10 columns for each potential digit that the images represent. And you'll see on those, I'm jumping ahead now, but you'll see on those 10 columns, we're not going to have digits, we're going to have like probabilities for each digit, right? So the first column, say it's going to show first image, so first row, first column for the first digit is going to show like 0.2, so it's a 0.2 probability that's a 0 digit. Then again on the first row for the first image, second column, say it will show 0.4, which is 0.4 probability to be a 1 digit, because we'll go 0, 1, 2, 3, 4. But that's, we'll explain that later too. Now, because you have to add the bias on each column. I'm sorry, again, I keep confusing myself. You have to add it to the bias on each row, right? And then you have 100 rows. So essentially what broadcast means is like, it's like a thing that internally Python does. It's just going to broadcast the bias vector, which is, one neuron, each neuron gets one bias, so the vector 10 neurons, when you have 10 biases, so it's going to broadcast it 100 times, so it gets added on each of the 100 lines. That's all there is there.
So on broadcast is only has to do with the bias.
Yeah, because it's it has to be broadcasted as many times as inputs you have. It's something you're never going to think again. It's pretty standard. I don't even remember from the code if you actually have to specify it as a code, or I think I'm pretty sure in TensorFlow it's built in. So when you specify the bias, the TensorFlow take care of that, map it to the X by W matrix. I mean, in TensorFlow you don't even have to deal with the matrix multiplication. That's what the TensorFlow does for you automatically in the background. But I'm not teaching this in this class, but you can actually practice. It's not very difficult to use NumPy. The NumPy, an American Python library, which is for manipulating matrices for linear algebra and stuff, and actually do the same operations with NumPy, like multiplying the matrices yourself, and there you would have to kind of broadcast it. But we'll just be using TensorFlow, which is like an abstraction of NumPy, and you don't even need to think about it in TensorFlow. But it's good that you asked, and I explained it.
Thank you. It makes sense now.
Yeah, and yeah, basically TensorFlow is like is the keras and the NumPy with quite a lot of stuff added on top of that, but that's the core of the TensorFlow library. Okay, and this is what he says, go deep. So just keep adding layers. Again, remember the same idea. You don't need 1 billion layers. You need enough to have like good classification, but you have to stop. You have to be as lean as possible, because the computations, as you see, like especially in all against all connected networks, which is what we've been talking so far, the computations increase like, I don't know, exponentially or more than exponentially, hyper exponentially. I don't know, but they definitely increase very fast as you add layers and corrections. So you have to be very lean for that.
Professor.
Mm-hmm.
I think you just mentioned that 200 are the layers, but instead I think you mean they're just neurons, the dimensions instead of the layers.
Yeah, 200 neurons per layer. Yes, that is correct. Sorry.
Oh yeah, I heard you said 200 layers, so I heard it right.
But there's neural networks which they have 200 layers. They actually have like thousands of layers too.
Yeah, exactly. But yeah, I mean just for this 200, I thought you mean the layers. The number.
This one is actually 5 layers. First,
yes.
Just to make it clear for everyone, 5 layers and 200 neurons on the first layer, 100 on the second, and 10 on the final layer. And remember that the final layer has to match the number of classes we have. Here, 10 classes, 10 digits, so it matches that. And we call it final layer, and it doesn't really have to do with the output neuron layer. There's no output and input when we call it in here, right? It's just a regular layer which does the summations. I mean, if you want to call it final, that's fine for me too. Okay, so do you have another question, or should I go ahead?
I'm good. Thank you.
Okay. So activation functions, we touched upon this before, and I'm going to also post material with a list of functions there, about 10 or so for you to see. The sigmoid, we've seen it before. That's down here. I don't remember if we've seen the relo function, but that's basically the one here. You can tell from the graph what it does. Basically, if the logit is negative, it just gives you 0, and then if the logit is positive, it just increases, I guess, linearly, right? And that's all there is to it. So this is relo is actually a very common function that is used. The whole idea again about the functions, we're probably going to do a lecture onto that if I gather enough material, is to choose the right function to have because those functions is the non-linearity you introduce in your networks. So you choose the right function for the type of data you have. And let's explain. Please interrupt me if, as I'm scrolling, like things get messed up or you cannot see it. So I'm sure that you're seeing clearly what I'm explaining. So the softmax function, and then we'll get into the loss as well, and then we can take a break. So the softmax function, which I think we've seen before, but we'll see now quite a lot, essentially is a function which it's non-linear as well. But the reason it's important here is because, and it's always used at the final output layer. I don't know what would happen if you use it in one of the internal layers. Maybe if any of you know, let me know. Maybe I've seen it before and I forget, but we always use it in the output layer because what it does, it just maps the predictions as probabilities. And it has a definition here. You can read it. I'm not going to go into much detail, but is what I mentioned before. And to just say it once again, is that when you get the predictions, and you have to think like how we do the loss, right? It's not going to tell you, I predicted being as 1 or I predicted being as 2. It actually going to tell you that I predict the probability, and the probabilities they go from 0 to 1, right? You can map it in your head to like percent, that's 100. It's the same thing, but it will tell you I predicted with 0.1 probability to be a digit 1. I predicted with 0.3 probability to be a digit 5. So that means 10% probability to be digit 1, 30% probability to be a digit 5. And the way, I don't want to scroll up again, I'm afraid to mess it up, but the way this works, you get in the output one row with 10 columns for each input, which contains the probabilities, right? So we had 100 inputs, 100 images, and the way you would get it is 100 rows with 10 columns each. Each column, so one row for the first image, 10 columns, each column having the first one being the probability of it being the 0 digit. The second one being the probability of this row for this image being the digit 1. The third row, the third column being the probability of being the digit 2. Because remember, and I'll explain it once again. So remember our digits, they go 0, 1, 2, 3, 4, 5, up to 9, right? So 10 columns. So in the output matrix, so it was the matrix that we saw before. We did the calculations, we added the bias. So that's a 100 rows, each row for one of the 100 images, and 10 columns, each column for one of the 10 digits, right? And then this matrix, we applied on each element the logit function, which was the softmax that we see here. And then what's this going to result into is into these probabilities. And again, let me explain it once again. Let's get the, and I need to do, you know, my Blackboard thing in the back because I have this fancy Zoom camera and stuff, but we'll do it eventually. If I had that, I would be able to draw now, but let me explain it once again. And then if it's not clear, we'll say maybe I try to draw it or you ask questions and we'll figure out. So out of this output matrix where the softmax has been applied, let's get the first row for the first image. And the first column for that first row corresponds to the digit 0. And it's going to have a number there, which is the result of the softmax being applied to the logit. And that number, let's say, is 0.05, which would be probability 5% for being digit 0, that image. Then on that same first row for the first image, let's get the second column. So that would be the probability of that image being a digit 1. And let's say that would be, the number there would be 0.1. So I mean, it has 10% probability of being digit 1, and so on and so forth. So let's say, I'll ask it as a question for row 50, column 6, row 50, column 6 of that matrix. For which image and for which digit would that probability be? Somebody tell me.
It'll be a 50th image for digit 5, right? Because
so
column 6.
So 50 row 50, column, what did I say, 6, right?
Yeah, I think you said 6. So it'll be digit 5, right?
Digit 5, and then which image? 50 image.
The 50th, yeah.
Yeah, 50th image, digit 5, because we go 0, 1, 2, 3. So the 6th column is going to be for digit 5. Okay, let me ask once again, and somebody else answers. Let's say 80th row, column 9. Somebody else.
I think that's the nice, the probability of the nice digit for the column. But the rows, I think they really it also depends if your samples are in the order or not. I mean, yeah.
So that would be the 90th. Did I say 90th row? So it would be the 90th image or 80th row. It doesn't matter. So let's think of it as images, right? The 80th image, and then which column? I said the 9th column. So that would be for digit 8, right?
Yeah. If you start with index 0, that'll be digit 8.
Yeah. So yeah. So let's say we do it like 0, 1, 2, 3 in order. Yeah. So that would be digit 8, because so that's digit 8 is the 9th column, and then the 10th column is digit 9, because first column is digit 0,
yes.
Second column is digit 1, third column is digit 2, and so on and so on. Okay. All right. So anybody else like confused with that? You can actually see it in the image I'm showing now. And this is exactly what we're discussing before.
Okay, I think I just want to make sure I understand correctly. So we just covered, I don't understand the row part, like 80 or whatever, but I understand in Python, the index is starting 0. But other than that, I don't understand the discussion we just had.
Okay.
And also, yeah. Mhm.
So let me go up again. Hopefully it doesn't blur out. So the discussion we had, it just stems exactly from this matrix, right? So what did we have as a row in each of these matrices?
The rows are different images.
The rows are different. Do you understand this, Junho?
Yes.
Okay, so essentially it's the flattened images on this row. And we had 100 images, right? So we have 100 rows here corresponding to the 100 images. So when I say the 80th row, then I would mean the 80th image. Does this make sense now?
Yeah, but what were you asking to, like, I don't, like, what's the, like, extra question with that? Because I understand that part, but.
So when we run this matrix, the input matrix on the neural network with a single layer, we ended up with what was the dimension of the final matrix? I mean, it's only one matrix multiplication. I mean, I'm sorry, one matrix. So what was it was a 100 by 10 matrix, which you can see here. Because we had the 100 images times 84 as input matrix, our weights matrix 784 by 10. So we ended up with a 100 by 10 matrix. And the reason for that being 100 rows, each one for each image.
Oh, I understand now. I understand what you mean by what we were discussing. I actually have a.
Let me actually say that so everybody else hears it. So 100 rows, one for each image, and 10 columns, each column for one of the 10 neurons, which we had in the final layer. And we said like 10 neurons because the number of neurons in the final layer, it has to match exactly the number of classes that we're trying to predict. So essentially we can say one column for each of the classes we're trying to predict, which is the number of neurons we're using, because the number of neurons has to match the number of classes. So it's 100 by 10 images. That's all there is to it.
So this equation doesn't even have this model. I mean, this equation depicting a model that doesn't even have any hidden layer. It just
it's only one layer. Yeah, exactly.
Okay.
Yeah, so it corresponds to the other one. Scroll up, but it corresponds to the one before, and it doesn't correspond to the code because in the code you was just throwing some other layers with 60, and then it doesn't correspond to this one either because in this one he's throwing some other extra layers as well. I shouldn't complain because we should be grateful that we have this nice graphics published by Google, so we can we can use them and save time, right? Use more time in the discussion instead of drawing. Okay, so we explained the softmax.
Oh, can we know also for the softmax it has a lot of mathematical term. What is the L1 norm?
That's a good question. It says the sum of absolute values, and I think that's, as you see here, that's this one. So yes, so the two lines, they mean absolute, right? I think it's not exact, it's sum of the exponents. So because the L is the logit, right? He uses capital L for the logit. So I think what he does here is like he gets the exponent of the logit, and then the absolute values of that, and then he just adds them up. So that's what's in the denominator, the added of the exponents of the logit values, and then that's the norm part, the normalization, because you divide by that, so you just normalize everything to be in the same distribution, right? So you divide, and he doesn't mention that in the text that you have the exponent of the logit, but that's what the formula shows, and that's what the softmax function is. So you get the exponents of the of each logit, and you divide by the absolute sum of the exponents of each logit, right? So you just normalize it across the whole set of logits and use a normalized distribution essentially. That's why you have them in the denominator. And I think that's the furthest we need to explain it, and that's the term we use in
So
the
that
L1
double bar thing around surrounding to EL
Mhm.
it gives you it. What does it return? It returns the no, like a normal distribution. Some of the I'm sorry.
Usually use single bars for the absolute, but I think double bars, I don't know. If somebody knows, please contribute and let us know. But it might indicate also the summation. I can look it up, or just Google it and do like double bars. What does it mean? Even though sometimes mathematical notations they use it a little different contexts, and I don't know if it's the right one he's using there. But I explain what it is, right? So, but the key
in general,
Mhm.
I'm sorry to interrupt. So
No,
like
sure,
in
sure.
general, we have like a L1 norm, L2 norm, or in general like LP norm.
Mhm.
And the LP norm would be that you would make everything to power of P and sum
Mhm.
them up and take the root of base P. So for L1 would be exactly the sum of absolute values. For L2, which is like L2 regularization, we would do like a square root of sum of squares.
Okay. And you'd still use the exponent as well for each logit, or?
Like this is the general definition for LP norm, which is not related to the exponents. But in here, I think this is doing the, like applying the L1 norm to the exponents of those things.
Okay. That's great then. That's great. And then, yeah, I think we also see it when I go back to pulling the material from the text and we get back into the math definitions again. I'm pretty sure it's covered in there, so we'll clarify. Okay, perfect. And then that's where I've been mentioning it before. That's the computed probability. So you can see, let's say for image 1, the first row, the 10 columns here, and it has those decimal numbers, which is 10% probability to be 0, 30% probability to be 1, and so on and so forth. And then you can see clearly that the highest probability for it to be is a 6. Okay, so where are they? Like 11:45. Let's take the break now. Somehow the last time I looked at the clock, it was like 11:25. Now it's 11:45. I was hoping to get the break at 11:30, but oh well. We'll do let's do a 10-minute until the 11:55, and then we'll have enough time to continue. Let's also do the attendance now. So if everybody could turn on your camera, and I'm gonna take a screenshot. I mean, enlarge the zoom so we can see everybody. Okay. The snipping tool. Okay. Let's wait for everybody to come online. And then Ariel, Nusrat, Tamzid, I'm sorry. Okay, so we have everybody. I guess there was a little delay. Shvantel, do we have you? Let me save it. Let's see. So we're like 2, not counting me, 2, 4, 6, 8. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 29. So there's some people missing. Third, including me. Okay. Okay. I took my screenshot. So you guys can turn your camera off and go for the break. And I'll see you at 11:55.
Professor.
Yeah.
Did you get me? Because my camera turned on a bit late.
Yeah, I got you. I got you. So I
Thank
see
you.
you now too. So yeah, no worries. I'll remember. No problem. So forget that. Microphone good, camera good. Okay, so you see now the gradient descent, and I'm just going to talk like just 1 minute about it because we're going to have a big load of it on the when we get to the back propagation with a lot of mass. So essentially, what he says here is like you know, if you plot the cross entropy times the weights, and of course there are multiple 10 weights, so it's going to be a I guess 11-dimensional graph or 10 weights, but he just pointed for 2. So essentially, each you know, for 2 weights, you know, you get this 3D graph, 2 weights times the cross entropy. So it shows you like as the weights value change, how the cross entropy loss function. It's just a loss function. We'll get into more detail in it when we get into the math. It's just a loss function like the one with the squares that we've seen. So you just see how this loss function gets minimized as you reach certain values of the weights, right? And for the values of the weights that this loss function is minimized, that's the right weights, right? Because you found a weight which minimizes your loss, and that's the weight you want to keep when you say you have trained your model and you finalize it, right? And you know, it's not as simple as it shows, because again, there are multiple dimensions, and also you can see like there can be like multiple paths into it, and you know, this is called like the landscape. So you have like the mountains and the valleys, and you know, you want to reach a valley. Of course, there's a trick, like as you're exploring the landscape, and you'll see when we get into the math, what happens there is that you know, we get partial derivatives of the loss function in respect to the weights, and you'll see that also there's mention of the fact that you know, as we minimize, essentially we're trying to minimize the loss function. When we minimize the loss function, we might reach a minimum where we get stuck, and I guess it doesn't show very well here, but imagine like being another like deeper valley, but you know, you get stuck in this valley, and then you wouldn't be able to reach the lower valley, which would be like less error and better weights, basically. So that's all these show. So essentially, you know, finding, if you will, I mean, the landscape shows you all the combinations possible between the weights. Only 2 weights here, but we have 10 more dimensions. So build regularized model. I think everybody can see the link of the website. Yep, so you can see in the browser, and then the link that Junho sent, everybody can see. And that's what we're looking right now on the screen, so you can open it if it doesn't show clear on mine. So what I was saying was that, yeah, you see 2 weights here. It's going to be 10 weights, and it shows the whole landscape with all possible values. But essentially, this line here is what you, let's say, walking through as you do the epochs. And the stars that he has here is the point where we are in each epoch, and then we move to the next one, and then we move to the next one, and to the next one. And this is a process again, which happens with the back propagation. We get the partial derivatives, and it's a stochastic algorithm, meaning that it can take one path or the other. But you know, I think, you know, we don't want to get too much into the computer science of these things. It's an optimization algorithm, which means like you know, you're just going to go towards a minimum of the error. Okay, so we're just going to stop at that with this definition, because another thing I want to cover today is the convolutional neural networks. Kind of go into one more level of complexity. I mean, it's not really complex if you really understand the structure of it. But the convolutional neural network, CNN for short, is a very common one we're using for image classification. And you'll see in the paper I posted, let me switch here. So that's a paper which we're going to be posting on the Blackboard as a homework assignment with questions. I'll probably go a little bit over it towards the end of the class. So yeah, so let's go to the convolutional neural networks. I mean, here it says the coding, which we're not going to cover now. But let me actually mention one thing that we see here for those plots. So basically, that's the number of epochs and the loss. And obviously, you see the loss being minimized. So there's actually two graphs here. The blue line is the loss for the whole sample, and the yellow line is the loss for the validation. Remember, we said, like, say, if we had 100 images, then we train the model with 90. So for all those images, we have the image and the label of the image, what kind of digit it is. And then the validation data set, we keep, say, a percentage of the input data set, say like 10% or something. And that's the validation one, which we know the labels, it's known, but we pretend of it to be unknown. So in the sense that validation is like you train the model, and then you throw in the validation data, and then see what the model predicts. So with the validation data, you pretend it's unknown data, so you throw it in, and say for one image, it predicts that it's 5, but you know the real label, and then you know, from the real label, you see that's 5, so that's correct, or you see the real label is 6, so that's incorrect. And that's goes back to false positives and negatives positives that we examined before. So that's what the validation plot is modeled after. And you'll see as we do the training, both of them increase. Now, and I'll show you another website, the Google TensorFlow Playground, where this shows well. I don't know here, I'm a little confused why it shows 10 epochs, and then the loss is like twitching, if you will. I mean, if it showed like 1,000 epochs, this would make more sense. And the reason I'm saying that is like, and I think I mentioned it in one of the previous discussions we had, that and that has to do also how you explore the landscape that I just showed before, and trying to find the minimum. You know, the landscape has like it's like a regular landscape on the earth, right? It has many like little hills and little valleys and big hills and big valleys, but overall you're just trying to go down the valley, from the mountain being the higher error to the valley being the minimum error. But on the way you're gonna go, you go over like little bumps here and there, and that's what this twitching of the loss values are. But that usually would appear if you have like a lot of epochs. Maybe I cannot click it in my head right now, but I don't know why for 10 epochs it would twitch. Somebody has a suggestion?
All the samples in the epochs. So between each epoch, let's say between 4 and 5, it might say for all the samples, it just plots all of them.
Okay. I think that might be it. So between 4 and 6, you have plotted for each of the 100 samples, and then it connects them with lines. Yeah, I think that seems like the right explanation. So you have 100 samples here, 100, 100. Okay, perfect. I guess I'm used to seeing it otherwise in when we do the big training epochs, and I didn't thought like we plot every samples. I think some of the plots, when you do a lot of epochs, for each epoch you just average the loss for all samples or something like that. So you just plot one data point for each epoch. But you know, when you have 10,000 epochs, it's still going to twitch around, right?
Right.
So, okay,
Yeah,
perfect. Okay, go ahead.
I also think regardless of the plotting methods someone just mentioned, I think that also it might be the task itself is not as challenging as it seems like. You mean I mean it might be some like very simple data set, and the 4 or 8 epoch is already enough to you know, to get a good performance. And also it might be on the opposite side, it might be this task is just too difficult to really like predict. That's why this model just doesn't really learn something from the data. That's why it just reached the local minima. It seems like it reached the local minima already, but it's really not.
Yeah, I think in 10 epochs, yeah, it's probably done because it seems to flatten out. Yeah, I wouldn't be surprised for this one. But yeah, that's a very good observation. Yeah, I was just thinking more like, how do we plot here all the twitching and stuff? So okay, but anyway, let's go ahead for the interest of time.
Can we go back to actually the gradient descent, because I didn't understand the momentum part?
I don't want to discuss this in much detail now. Let me see if I can answer your question really quickly, because we will do the gradient descent in more detail in the next lecture. So mini moment. Yeah, I want to discuss that now. I probably, if I start talking about it, I probably confuse you even more. So let's skip it.
Okay.
I would say, yeah. But momentum, I think for me, it would be like the speed. So essentially like how fast you go to reach the minimum. All right. I think that's what it is. And probably momentum is a measure to quantify how fast you reach this minimum down here. Because when the momentum slows, it means like your curve is flattening, so you reach in the minimum. So I think the momentum, if I remember correctly, I have to read it up again before I lecture on it. I think it's a measure for reaching the plateau and the learning having to stop because you don't improve anymore and have reached the valley. That's what I think. It's kind of the momentum, you know, how you go down the hill towards the valley, right? As you reach the valley, how you are like rolling down the mountain, you kind of like start slowing down, I guess. So hopefully that answers the question descriptively, but we'll see it in more like mathematical and technical detail. Okay, so let's talk about convolutional networks now. And I'm pretty sure some of you are familiar with it, but we have to explain in detail because not everybody is. Should I start? Yep. let's start by this one. Okay, so obviously what we see here, and please let me know if it comes like blurry or anything like that. We see an image with the 3 layers that we discussed before, but we kind of see this sliding animation on how we compute the values or feed the input from the values that's on the image on the neural network, right? And if I am to say in one sentence, the reason why this is being done is because we're moving away from like obviously we have like 3-color, 3-layer multi-dimensional matrices, tensors essentially for the 3-color images, and you can have many more layers as well. But we're also moving towards like real images, and real, you'll see in the paper, this applied exactly on the DNA data to more complex data than the simple handwritten black and white digits. And of course, those more complex images and data, I mean, for the DNA too, essentially, it's just a trick that you convert with the one hot encode in the DNA data to look like an image, and then you just follow the same thing like you would use for image classification, whether it's a cat or dog. But the thing is that again, compared to the black and white single digits, images have more features, and that's what the convolution process, from a practical point of view, is designed to capture the more features on the images, right? Because a dog or a cat, when you try to classify it, I mean, now the algorithms, and we'll see a simple example when we get into the coding with TensorFlow JavaScript even, that it predicts whether it's, it predicts the breed of the dog actually. So you can imagine how detailed it is. And, back to what I was saying about the features of the image, the different breeds of dogs, they have like long snout, long ears, whatever, short legs, long legs. So that's the local features, on the leg area or the head area or the ears area, that this convolution process is designed to learn and then be very detailed in automatically categorizing the images, right? And the way it does that is with the convolution process, which is this sliding, we can call it matrix, but essentially it's a filter, this sliding filter over the image. So again, we have our code here as I scroll, but we're going to skip the code for today and just focus on the structure. So very abstract here, and I have a couple more pages with explanation for that, but let's simply focus on the structure for now. So
I have a question about the DNA sequence CNN that you mentioned. So in that case, do you use a 1D CNN network, or how do you, like, because obviously image is 2D image, but your convolution filter uses like 3x3 or something like that, but like DNA is like
so it is explained in detail on the paper. We're not explaining now, so I'll send more as a homework. But you don't have like 3D tensors as you have the layers of the image. Here, like the 3 colors, you have a 2D image. So essentially, you convert the DNA in a single layer 2D image with a one hot encoding. By essentially your the one dimension of the image being the 4 bases. So it's actually a 4 by whatever length your DNA sequence is. So if your DNA sequence is like 100 base pairs, so you convert in a 4 by 100 image. But it's always 4 because it's the 4 bases which you one hot encode. So that's basically it. It's explained in quite detail in the paper. Yeah. So and again, as I said, like once you can do that conversion, then the whole process is exactly the same. So that's a lot of the stuff that happens in bioinformatics. That's why I like to go more. There's not much to explain, bioinformatics is a lot of applications, right? You just get you just do like a data mapping, and then it's exactly the same with all the foundations we're discussing. And that's what we're focusing in this class. Okay, so a convolution process. One thing that you see here before we go into the process in detail, and one thing you should remember about the convolution is that you might start, say, with a 4-layer image. Some modern digital images, they actually have red, green, blue, and magenta. So you can have 4 layers. And then those layers can increase. I mean, it's an artificial increase, but essentially what that goes into with the convolutional neural networks is that, and you might have seen like, let me see, I'll show you the image now. I switch window. Let me know if my switch window doesn't show clear. Please always tell me. But what those layers, representation is a representation of the local features of the image. Let me see if I can get some stuff. Okay, there you go. So those layers that you see in there, of course, the image again, it starts with 4 layers, but we end up with different dimensions, and we'll explain how that works, but with many more layers. But essentially inside the computer, like this is kind of what it sees, right? Kind of like this crazy abstract art. And we'll explain that again, but let me see if I can find a better one here. 2nd layer presentation, 3rd layer. There's actually tons of links, right, that you can see. But essentially, these internal layers that we create capture different localized features of the images. I guess here, whether it's like noses or eyes or eyebrows or mouth, and I guess if it's a landscape picture or a dog picture, capturing the snout and things like that. So that's the reason we create the artificial matrix layers inside the convolutional neural networks, and that's the power of the convolutional neural networks, that you create those layers. And don't be confused with neuron layers. Now we're talking about convolutional layers, and the filters and those layers are designed to extract the features from your image that you need for classification. And let's leave it at that for definitions, because we'll come back to it in the convolutional neural networks, since they're so central in machine learning, artificial intelligence, and also in the bioinformatics applications as well. And we'll do the back propagation, but also we're gonna explain in more detail the technicalities of the convolutional neural networks, their the maths and the theory behind it. So you'll get the whole picture. Now we're just doing the introduction today. Now a little bit for the dimensions, and this is just an abstract schematic, but I would say, like, I'll post all those pages. Definitely bookmark them, because when I was started with the convolutional neural networks, I refer to them as CNNs from now on. I was really struggling to debug my code because I haven't understand this thing here. And this is like the dimensions you specify going from one layer to the other. And I hope I don't confuse you. So when I say convolutional neural network layers, I refer to those matrix layers here. But when we're discussing about the layers of our hidden layers, etc., of our artificial neural network, one layer of neurons is this one layer of neurons is this one, and one layer of neurons is this one. Because remember, each layer of neurons it just processes matrices, right? And that's all of that is stacked up matrices. So one layer of neurons process this stack of matrices, the next layer, hidden layer of neurons processes this stack, and then the other layer processes that one, right? But always when you do, when we get to the coding, it's always tricky because if you don't specify the dimensions right from one hidden layer to the other, then Python always complains, and I always had this problem, right? But it's pretty simple. If you remember it now or keep referring back to it, that's all you need. All right. So, and I'm pretty sure I'll verify and let you know that this matches like exactly the way that it's coded on the TensorFlow and the Python code when you specify your convolutional neural networks in the code. So the first one is the filter size. Filter size meaning like, how does it have it here? Shows a, well, let's look at this one. First one is the filter size, is the sliding filter that you saw in the animation before going. That's the 3 by 3, right? 3 by 3. The second one is the input channels. Another little different term like red, green, blue, 3 channels. Maybe it clicks with you, but you know, maybe it's confusing. Here it has red, green, blue, magenta, supposing that this is a digital image with 4 layers that came from the sensor. So 4 input channels, again, 3 by 3 being the filter that slides over the image to do the convolution, 4 layers in the image, and then how many layers the next one is going to have. And then another way I could call that is like how many filters we're going to have, because remember I mentioned each layer is created by the convolution operation, and it's a kind of, I mean, that's the filter, but I could call each layer being a filter, or if you want to call it something else, each layer capturing a specific characteristic of the image, right? Whether that's the long ears of the dog or the long snout or the short snout or whatever. You know, you adjust how many layers you want to have on the next one, depending on how complex you think your image is going to be. And then again here, how much here we apply different size sliding filter. We want it to be 2 by 2. And then the actual layers on this level, and I think I need to get probably my terminology a little corrected, because I don't want you to be confused like layers of neural networks with layers in the convolution. And we'll figure out how to call those stacks here. But this would be a convolution, our neural network with 3 hidden layers, and then we have the convolution layer on each of the hidden layers. But let's leave it at that now. Okay, so then in the next one, so here you use a 2 by 2 filter, and then your input channel, which is this one, with 6, and then your output channel is going to be 10. That's why you're creating 10 here. So from those 6 layers, you would want to refine more and capture more subtle features. That's why you increase the number of layers there. And then at some point, this has to come together to the number of classes we want to predict. And we'll see quickly today, because we're kind of running out of time. Yeah, to come down to the number of classes, right? Like it always comes. Okay, so any questions regarding that? I mean, it's just terminology here. No, okay. So this animation, let me see. I think the next section explains it quickly, but this animation is what we've seen before. Okay. So I don't know why he skips ahead on the final part. But I think that's the one I wanted to explain. Okay, so here, let me enlarge it a little. So where did I have? Just give me one quick second. This is just code. Okay, so see here again the features that I mentioned, right? So this is one filter that's designed to highlight the vertical images, the vertical lines in the image, and this one is a filter that's designed. I'll tell you how this works. That's designed to highlight the horizontal structure of the image. But I had like what I'm trying to see is like this one. Yeah, okay, so that's what I want to show. Did I just stop my my sharing? I'm sorry about that. Can you guys see my shared screen?
Yes.
Yes. Yep.
Okay, perfect. All right, so let's use this one really quickly to explain you know, how things work. This is you know, a handwritten digit. I mean, you can apply convolution to that stuff as well with the pixels and the gray values of the pixels that we've seen before. But what I'm interested is to use this animation here, which shows like how the convolution process works and what you get in the next layer and so on and so forth, right? So, and I'll tell you more about this filter in a little bit, but this filter is composed. It's a sliding filter, as you see, and it slides over the image, covering all cells of it. You can adjust parameters like the stride, which means like how skippy it is as it slides through the image. See, obviously the stride here is just one, so it just slides one over and then one more over until it reaches the end. There's another terminology called the padding, which is padding the image with zeros on the outside if you want that thing to capture what they call edge features. So it's just going to slide a little over one or two positions to the edge if you want to pad it with one or two padding positions. Padding usually is 0 to indicate that you're outside of the image. But you know, imagine that thing like sliding off and you add like 2 columns of zeros. It's still going to capture like the last edge feature that you have right here. But sometimes you do that, sometimes not. So that's what the padding is. Basically what happens, as we're going to see down here, is just our usual matrix multiplication. And I'll show you another page. I'll explain this formula here, and I'll show you another page to understand what does this matrix multiplication does. But it's a pretty standard matrix multiplication. So that's our image with the values that we have on the pixels. I mean, it shows letters here, not numbers, to explain it more clearly. Sometimes you call it the filter, sometimes you call it the kernel. It's an interchangeable term. So you apply the kernel on the first, and then you know it's going to slide one over, and then it's going to slide one over, and so on and so forth. But when you apply, this is all, it shows letters, but this is all numbers in there. But this is a good graphic, that's why I chose it. But essentially it's like the typical matrix multiplication, right? So in the first one, you're going to be how do the matrix multiplication, the row times the column, right? And again, the row times the column. So it's going to be AW plus BY, and then AW plus BX, and then EY times FC. Actually, this one, I need to double check. This is not actually a regular matrix multiplication, row by column. You just, and I think that's the case. So we should, I'm pretty positive. I mean, so many things I talk about, I just miss the definitions. It's not matrix multiplication, you just multiply the cells. So, and that's what you see here. Again, the cells are numbers, not letters. So you multiply A by W, and then B by X, you add those, and then E by Y, and then F by Z. So it's not a matrix multiplication. You just multiply the cells that it touches upon, right? So that's what you see here. And then when it slides over one, so that thing here, it's going to slide over, then it's B by W. So imagine that gray thing, it just slid over once, stride one, and then it's sitting on those 4 cells. So you will see B by W, and C by X, and F by Y, and G by Z. And then it's going to slide one more over, and it's going to be sitting on those 4 cells here. So then we're going to have C by W, and D by X, and G by Y, and H by Z, right? So no matrix multiplication, scrape that. It's just, you know, the cells that it slides over, it just multiplies it. And you'll see in the next picture how that works. Now, what we want to see here is this formula where we have a 4x4 image, small image, 4x4 pixels. It's just an example. And we slide over it a 2x2 kernel or filter, however you want to call it. And then we end up with another image called activation maps. So essentially, the stacked stuff that we were seeing before, that we're going from 4 to 6 to 10, the official. So also, let's change the terms now. I call them layers. We'll call them activation maps. My mistake, I didn't use the right term. So layers always for neural layers, activation maps for the for those stacks that get increased or decreased as we do the convolutional network. So our image was 4x4. Our kernel or filter, however you want to call it, was 2x2. And we ended up with an activation map of 3x3. So from 4x4 to 3x3. And we'll see how that works with the formula above. Now, each one of those stacks that I was showing in the previous slides, it's an activation map. However many activation maps we end up with depends on how many different filters we apply, right? So if we have like 10 different filters, and we apply them like doing this convolution process like 10 different times, we're going to end up with 10 activation maps, right? And that's, I'll go back to the previous slide as well and show it. And again, one key thing to remember is that you use as many filters as you need to capture however many subtle features you have in the image. So for example, say you want to classify breeds of dogs, and you know that the breeds of dogs, they're based on like the length of legs, the length of ears, the length of snouts, and the length of tail. So 4 features you want to extract from your image, you want to design 4 filters. And those filters are designed in the sense that it's basically like what the model designs is the learnable parameters in the model. So it's exactly the same thing like weight. So those filters essentially is weights, right? It's just applied in a different way. Instead of using the lines that we had before, we use a sliding convolution process. So it's a different mode of thinking, but that's the learnable parameters in our model. And again, we'll get in more detail in those definitions. Now we're just doing the introduction of the convolutional neural networks. Now, to what I was saying before, from the 4x4 image, 4 pixels by 4 pixels, applying a 2x2 filter, and then end up with the 3x3 activation kernel. This is what this formula gives you here. So if you have the input size, the input is always going to be a square. I'm sure there's non-square images down there in this convolution process for non-square images and formulas for that, but we're going to stick to the square ones for explaining the class. So it's a 4 by 4. So you know, it's a square. 4 is what you put here, minus the spatial size of the kernel or the filter. So that's a 2 by 2. So 4 minus 2, that's 2, plus the padding. So here we have no padding, so it's 0 padding. So it's like 4 minus 2 plus 2 times 0, 0. So that's 2 up here divided by the stride. So our stride, as you see, is like 1 because we just have here, we slided 1, and then we slided 1. It could be 2, so you just do bigger skips. So we have 4 minus 2 plus 0 divided by stride 1, that's 2, plus 1, 3. And that's the 3 by 3 of the activation map, which is also square. So that's what this formula has. Like a simple formula, you just plug the numbers in, and you get the output. And that's basically, let me see if I have to explain anything from here. I can leave this one, that's all I needed. So if I go to my previous picture, we'll put as a homework to plug the formula in and predict like what's going to be the number of the size of the activation maps you're going to have in the next layer. So again, this is our image. Now we show it 28 by 28. We go into our previous discussion, and then we apply the 3 by 3 activation map, and then the size was a 28 by 28, so the W was 28. The F was 3, and then I'm not doing the numbers now, I'm just mentioning. And then the padding, assuming that he did like he didn't go over, it was 0. And then the stride S was 1, assuming that he just skipped 1 at any time. And then if you plug the numbers in, you'll get like I guess the results again 12 and 28 by 28. That's interesting what you get from the formula. And then he applied 12 filters. That's why he gets 12 activation maps here. And remember, each activation map is designed to capture a specific, well, it's not designed, but actually you design your model to have that many activation maps that you think is going to be the different features in your image. And then as your model gets trained, those activation maps are going to fill with values, which again is kind of the weights. I guess the weights is on the filters, but then you know, the weights on the filters are going to be learned as the model gets trained. But then you're going to have, you design your model to have enough activation maps and enough space in the activation maps for your features from the image to be filled in, and then essentially the features to be captured. And when I say features, I mean like numbers, right? So essentially, the convolution process is getting the pixels from your image and applying the weighted filters on them, which again, the weights of the filters are being learned, and extracting the features of the image and filling, which again is numbers, because what we're doing inside the computer for the representation of the image is numbers, and those numbers they get stored in these layers. But it's the key is like that you design the right size and the right number of activation maps. I keep saying layers, the right number of activation maps to capture all the features on your image, and having the right structure for your model to extract the feature of your image and do the right predictions. I mean, we have a lot of things to still talk about those, but you know, that's the very general idea. Let me find the other thingy I wanted to show. It was a nice one here. I don't know if I was able. I think that's the one. Okay, so one thing, last thing I want to explain about the learnable feature. So how does this work, right? I mean, here it shows like a little mouse which has some curves. So what are the features of the image here? Is the back side of the mouse, right, which is this curve. It's the ears. Obviously, it's a very simple image as a educational example. The ears, which is like the two circles, and maybe the tail and the eyes, and so on and so forth. So this is one of the filters we saw before in its pixel representation. So you see here everything is 0 except some numbers which have some value, right? And those will be learnable numbers that are kind of like the weights we discussed before, which they will get trained as the epochs of the training progress. So essentially, what this is designed to capture is exactly that curve, because so that filter extracts the right side curves, if you will, features from the image. And the way it does that is, again, because it has everything 0, and then it's the areas which is kind of this curved area with the numbers, which is the non-zero numbers, is the ones that will get amplified in the image, and everything else is going to get set into 0. So that's how the filters work. They filter out everything else besides the right curved lines in the image, right? And this is an example of one feature in the image, and that's what the whole convolution process is, to extract through this, a matrix multiplication process all the feature from the image and store them in, because you saw here, where was it? As you were going through it, it was I was just doing the multiplications, so extracting those features by just amplifying the horizontal lines or the vertical lines or the curved lines, and just storing those features in the activation maps that you generate as you go through the convolutional network. Okay, and I think that's where we'll get back into it, like I would say at least 2 more lectures, both the practical aspects and the theory, plus then the coding. But I think this is enough for today with the convolutional networks, and I'm sure like you're probably a little confused too. But I think also you have like sort of a seed of what the thing is and how it works. Yeah. And since it's 12:45, let me, I'll stop the lecture now, and let me open it up in questions regarding the convolution networks, and then we can wrap up. So questions you have in regards to that?
So in an image, it's easy to see for me why you would apply certain filters for feature extraction, but when it comes to maybe not image but other data, or is this like solely for image data? But how do you define, your kernels for?
So, for example, let me go to the paper that we're seeing here. It's all it's better, I would say, think of it, everything is being images, and stuff which are not images, you just map them into images. So for example, let me see where this graphic is. Does it come figure 2 with the DNA?
Yeah.
Okay, so basically what he does here, so that's like vertically is the length of the sequence. I don't know, let's say it's a so a DNA, right? ACGT.
Right. Oh, that's awesome. Okay. Yeah, everything makes sense already. But yeah.
So you do, let me explain it real quick. So you do the one hot encoding by putting everything like as empty pixels or 0 pixels and 1 pixels where you have the letter. and there's your 4 by whatever the length is, 50 image, and then you can do convolution into that, and so on and so forth. And then, you know, anything else classification you have, if we can map it in that structure, then it's all the same from there. Of course, you'll have to adjust like the sizes of your activation maps and the layers and so on and so forth. And you'll see here that we'll talk about activation layers. I mean, I have to stop saying layers, activation maps. But again, there's also the same concept of neural network layers and neurons that we discussed before, because basically, you probably figured by now, one neuron is one matrix multiplication and one addition of the bias, right? So essentially, yeah, maybe we'll talk like about multiplications of matrices in the convolutional networks, but wherever you see one multiplication matrix, you can count it as being one neuron, you know. So that's how we can transition between the two models. But in the code, you don't even talk for neurons. You just see specifying like sizes of the layers and the activation maps, basically. But you know, it's both part of the same game. Okay. So any other questions?
So is this CNN model like resolve this one-hot encoded map that we see that as an input, and it just scans it? Is there so I guess like we'll talk about this kind of like application in genetics later this course, like going into deep, like more into in depth. Are we planning to do that?
This is a pretty this is simple. It's a very simple application. Like I was mentioning before, you just, you know, map the data to an image and you just run it through a convolutional neural network. What I want you to understand is like more what's, I mean, the mapping is just like a 5%. It's actually, it's interesting, just doing a anecdote parenthesis here. In bioinformatics, the data, many of you might know, it's so messy that you might end up like spending more than 0.5% of the time, like sort of like getting the data in the right format. And I don't mean like doing this mapping here. I'm just saying like cleaning the data because it's so messy. And then the other 50% or less than 50%, you know, building your model and fine tuning it. Building means how many layers, you know, the parameters, how many epochs, and all that stuff, right? The functions, you're going to use activation functions. But what I want you to get out of it, you know, is how to build this kind of models, right? So when say you go do research on that or work on that, you know how to design the right model. It's always designing the model is always like a iterative process, because you start with something and then, you know, you have to fine tune it, add, remove layers, change parameters, and so on and so forth. But
well, I mean, I understand those are like that can be a little trivia, but I'm sure like the, you know, the size of the filter and what is predicting and how they design this is definitely, it's not easy for me, even though I just saw this paper. So I don't know, for me that might be like more challenging because I'm not bio background. I'm CS.
Yeah, we'll cover that stuff for sure. Yeah, but
what is it this predicting? Binding affinity? Yeah.
This one is for this paper. I think the example is transcription factor binding sites. So essentially, you have you know, your training data set where you have sequences where you know that they're positive for binding those two transcription factors that it shows there, and then essentially you train model based on that with convolutional neural networks, and once you have that model trained, then you throw the unknown sequences in, and then it tells you if a transcription factor will bind there with what probability or not. So that's what this model does.
Different samples with a different DNA sequence, and they have a label that they are binding, or whether they're binding or not. And is it what is?
Yeah. So you have the sequences and they have a label, and that's your training sample. And yeah, that's how it works. Of course, biology is more complex, because when we say like images train convolutional neural networks to recognize whether you have Labrador, or you have a hound, or you have a terrier, or whatever other type of breed of dog, that's it. It's just the dogs. We know it's a dog and it's breed. In biology, you cannot say like I got like some sequences and I'm training and predict transcription factors. It has to be very specific. Is it like sequences of human, and then it's going to predict human transcription factor of sequences. Then also like you might have to do, it's biology is very messy. You might have to do that you predicting transcription factors which are like transcription factor binding sites which are open in a specific developmental condition, a specific species, and so on and so forth. So there's a lot of stuff like that in there. So,
I mean, just for this model, I'm just surprised that they're looking for the binding site and binding affinity of this transcription factor. They're just looking at the DNA sequence, because I'm sure the binding factor is a protein, and that protein is binding to this DNA sequence. And I think what they're doing is regression, right? Not binary classification, whether it's going to bind or not. It seems like it's a regression model. How well is binding? So it will print the level.
Well, it's more, this specific one is more like signal recognition. So basically they build inside the model the DNA sequence signal for the binding. DNA sequence recognition, that's what is built in this model. So, but let me ask, because I see more people. Of course, we're done for the day. Everybody feel free to check out. I think some people check out already. I think they have other classes, but I didn't have the chance to say. You'll see it on the Blackboard. Like I'll post this paper with questions. I'll post the links from today and the lecture recorded with questions as well for the next homework. But we don't have any. I will add some. Definitely, I will add some supplementary text. But the main homework will be with what we saw today. But is there any questions from anybody else regarding the materials we went over, or the concepts? Okay, then if there's not, of course, we always have the discussion forum. We can conclude, and as much as I would like to stay in and discuss more with you, we have our department meeting starting at 1 in 3 minutes, so I will have to check out as well. So let's stop it here for the day. Thank you for coming, and I'll see you all next week.
Thank you.
All right, take care.
Thank you.
Thank you.
Bye-bye.